equation, we don't have like sometimes fraction.
A what?
We don't have a fraction.
Fraction?
Yeah.
Yeah, sometimes we need fractions. Sometimes we can balance it using fractions, but don't leave it that way. Do you want to do an example?
It would be nice if you can use the number.
Okay, let's do C 3H8. That one might not be one. Let's do C4H10 plus O2 gives us CO2 and water. Okay, so we have carbon, hydrogen, and oxygen. Who do you want to start?
Start with the beginning, carbon.
Okay, carbon has 4 on the left. How many on the right?
It doesn't matter we start with the carbon with any of
It doesn't. I like to start with the compound with the highest numbers. But yeah, it doesn't matter which one you start with usually. Okay, we have 4 carbons on the left. How many on the right?
1.
So what do we do?
We are going to divide it by
Well, how many do we need on the right?
both sides. We have to be
The same.
the same.
Okay, so how do we get 4 on the right?
On the right, divided by
No,
no. Divided no.
we just put a 4 right here.
That's it.
That's it. This says we have 4 carbon dioxides. And in one carbon dioxide, there's 1 carbon. That means we have 4 carbons. Do you follow?
Yeah, but we have to put 3 because one is already exists. 3 more 1 plus 3 is
1 plus, where's the 3? I don't know what you're talking
No, I
about.
said that instead of 4, we can put 3. Oh, no.
3 times 1 is 3.
3
4 times 1 is 4. So we got 4 on both sides. You following? Okay, how many hydrogens do we have on the left?
10.
10. How many on the right?
On the right, 1.
Careful.
Hydrogen, 2.
There's a 2 right there.
Then divided by 5.
Well,
2, 5 is
2 multiply what gives us 10?
5.
5, okay. All right, so far so good. Now we got to count the oxygens. Let's count the right side first because it's already balanced. So how many oxygens do we have in this group?
1.
We have 2 in every carbon dioxide. But we have 4 carbon dioxides. So we have a total of 8 oxygen atoms. Do you understand that?
Yeah, because this 4 is multiplied by 2.
Okay.
Which
But
is gain 8.
okay, do you get that though? And how many oxygens do we have over here in water?
And water, 1.
We have 1 for 1 water. How many waters do we have?
5.
5 of them. So how many total waters do we have?
Total water, 5.
5. So 8 plus 5 is 13.
Okay. Oh, 8 plus 5 is 2.
Do you follow? Or do you have a question?
8 plus 5 is 13. No, I got it. Thank you.
Okay. Okay, so we have 13 on the right. How many do we have on the left?
10.
Where's 10? I don't see 10.
Oh, no, 2.
Oxygens. We have 2. So 2 times what number is 13?
2 times.
Well, here's how you figure it out. You do 13 divided by 2.
13 divided by 2 is going to be 6.5.
6.5. Or we can just leave it as 13 over 2. Either way. And if we do that, 13 divided by 2 times 2, that gives us 13. So do you see how it's all balanced?
I know here it's 13.
But we can't leave it this way, so what do we have to do? Let's multiply all our coefficients by, what's going to get rid of that fraction?
Multiplied by 1.
Yeah. What number do we multiply to get rid of that fraction? get rid of the 2 on the bottom, so we multiply it by 2.
So
Do you understand that?
only this 2 cancel the 2.
Yeah, if we multiply that by 2, that goes away, and we're left with 13. But if we multiply that one by 2, we have to multiply this one by 2, this one by 2, and this one by 2.
All of them.
All of them. Otherwise, it's not balanced anymore, right? So you can balance it with a fraction. Just make sure you get rid of the fraction.
But if you multiply by 2, then the 8 will go to 16.
Yeah, so now let's recount them. It's going to be a different number, isn't it? Now there's going to be 8 carbons on the left,
And 10.
8 carbons on the right here. And we have 2 multiplied 10, that's 20 oxygens on the left. 10 multiplied 2, that's 20, sorry, not oxygens, hydrogens on the right. You with me? And then over here you have 13 multiplied 2, that's 26 oxygens on the left. And then you got to recount these. 8 multiplied 2, that's 16. And then 10 multiplied 1, that's 10. You add the 16 and the 10 and we get 26. It's still balanced.
Only the 2.
Does that make sense?
Yeah, when you put the 2, it's brought balance for it.
Yeah, if you multiply everything by the same number, it's still going to be balanced. Doesn't matter what number you multiply by, as long as it's the same number. We good?
Yeah, thank you.
Any other questions? All right. You're welcome. Okay, today we're going to do different types of chemical reactions. We're going to focus on 3 types, well, kind of. You can really focus on 5 different types, but there's 3 main types. Okay, so let's and I brought a bunch of demonstrations to help us to kind of, well, because it's cooler, right? All right. So, types of chemical reactions.
It's oxidation reaction.
That's one of them. Yeah, the first type we're going to talk about, in fact, I'll give you all 3 of them and then we'll talk one at a time. So, oxidation, reduction reaction. And if I put RXN, you guys understand that's reaction. Just a simple way to write it. I know it's not spelled correct, but okay. And another way to write this is redox. So if you see a redox reaction, that's an oxidation reduction reaction. Good? Okay, I'm going to just give you a few examples of each of these types, and then we'll go a little bit deeper into each one. Okay? All right, we also have precipitation reaction. In fact, let's just stick with one for a minute. I'll give you the examples, and I'll give you the other type, give you examples, the other type to give you examples, and then we'll go deeper. Is that okay? All right. So an oxidation reduction reaction, or redox reaction, is when electrons are transferred. What does that sound like?
Sounds delicious.
What? Covalent or ionic? Covalent share. So this transfer electrons is like ionic, right? So if we have an ionic, then we have a transfer of electrons. So for example, and we did this one, I'm not going to show this one again because we did it a few times ago.
When electron are transferred.
When the electrons are transferred, we have oxidation reduction. That's kind of how you tell if it's an oxidation reduction reaction. So first example, let's do is magnesium in the presence of oxygen. Now, if you just have magnesium sitting there, it's going to oxidize, right? Or iron just sitting there, it's going to oxidize. Well, that's why we call it oxidation reduction reaction. Okay, because one of them is reduced, one of them is oxidized. And we did this one. We took a strip of magnesium and we put it in the fire. Why do you put it in the fire? To make it react fast, right? You can let it sit there and it'll react, but we give it some energy and it's going to react faster. Make sense? Okay. And any ideas what it's going to give us? You should be able to figure this out right now. MgO. That's the equation. That's the formula. It's the only formula that we can write for magnesium oxide. Okay. All right. So this is an example of oxidation reduction. So let's kind of look at their charges for a minute. Well, what's the charge of magnesium metal? That's the charge of a magnesium ion. What's the charge of magnesium metal?
It's varies or sometimes
It's neutral. All elements by themselves are neutral. When do they become charged? During a chemical reaction. Okay? So the charge of magnesium is 0. What's the charge of oxygen gas? You guys ever get shocked by breathing? No, it's not charged, right? Any element by itself is neutral. We get that? Okay. What's the charge of magnesium in magnesium oxide? You guys said it earlier. 2+. And what is it for oxide? 2-. So we can see here that the magnesium loses or gains electrons? It loses electrons. And what did we say happened to the magnesium? It oxidized, right? So oxidation is a loss of electrons. And you'll need to know that. We'll get a little deeper into this, but just showing you. And some of them are a little harder to do. I'm only going to show you on this one because it's one of the simpler ones. Okay? Yeah?
So this equation doesn't seem balanced?
Oh, it's not.
Okay.
Yeah.
I didn't know if
We don't need to balance it because we're not trying to figure anything out. But if we are trying to figure out, okay, how much product can we then we need numbers. If we need numbers, then we have to balance it. We'll get to that next chapter. Okay? We learned how to balance it this chapter because we just started talking about equations or reactions. Okay? All right, if we take a look at oxygen, oxygen gains or loses? It becomes negative. That means it gained electrons, right? And so we call that reduction. Makes sense in your mind? Or goes against what your mind would be thinking? Right? When I was in this class a long time ago, I remember just talking about this, and this is oxidation is loses electrons. Okay, great, fine. Reduction is gains. Like, what? What? That's the dumbest thing I've ever heard of. Are you guys on the same page, or you guys like reduction is gain? Okay, so here's how I think about it. What happens to the charge? It goes from 0 to -2. The charge is reduced. That's way better to look at it. In my mind, what do you guys think? Or am I just goofy? No? Yes? Okay. So I'll just put on here, it's a reduction in charge. And if you want to remember which is which, here's this. Oil rig has nothing to do with chemistry, but oxidation is losing electrons. Reduction is gaining electrons. But I like to think of it, reduction is reduction in charge. Well, and if it has a reduction in charge, it did gain electrons. And we should understand that by now, right? I hope. Okay. All right, so that's one example. I didn't show you that one because I showed you a while back, right? So let's do some more. So another one is if we have H2O2. Anybody know what H2O2 is?
Just another example.
Hydrogen peroxide, the stuff in the brown bottles you stick on your cuts and it bubbles, right? Right? And when you do that, it bubbles. What's that bubbles? Formation of a gas, right? Tells us a chemical reaction is occurring. Anybody know what gas it is? Why do we use peroxide on our, what does our injury need? Oxygen. It produces oxygen gas, and it's still liquid. Well, there's water, okay? So this one might take a minute if you want to be, if you want to balance that one. Yeah. So this is another. So that first one, you have magnesium and oxygen, and you get magnesium plus oxygen, and you produce one compound. So we call that either a combination reaction or a synthesis reaction. You guys know what synthesis means? To make something, right? Yeah. So that's why we call it a synthesis reaction. Sometimes it's called a combination because you're combining something, okay? I hope it doesn't make a big mess. I brought this so that it wouldn't, but we'll see. You guys ever seen elephant toothpaste? Yeah, it's how elephants brush their teeth. You guys know? Oh, not really, but... And you could do this with the cheap hydrogen peroxide you get at the store. I'm going to use the better stuff. This stuff is 35%. What's the stuff you buy in the store? 3%. And if you want even more, a higher percentage that's pretty cheap still, you go to where they do hair salons and stuff. They have a 6%. Why am I putting soap in here? Because we're producing oxygen gas, right? You put gas in soap, and what does it do? Bubbles, yay! Okay. You guys don't like bubbles? Okay. And just to, I don't know if this will do a whole lot. We'll just make it colorful. Why red? Probably doesn't need that much, but okay. No one knows why red? University of Utah. Oh, you guys are all BYU? It's okay. I don't care who wins sports. I really don't. I just like you. That's where I went. And, oh, before I do that, this stuff will react without you doing anything. But, so we got to give it a catalyst. We'll talk about catalyst later. That's not what those are for. Oh, there it goes. So this stuff is kind of bad for you. That's why we just give 3% in the stores, right? Let's put some more in there. Mix that up good. And it's reacting right now, but it takes a long time. And can y'all see that? You will be able to see it more in a little bit. Hope it doesn't get everywhere. We'll see. Okay? So here's the catalyst. This just makes it go faster. This is a concentrated solution of potassium iodide. So a catalyst doesn't really participate in the chemical reaction. It doesn't change the product, is what I'm saying. But it just kind of gets it to go. Ready? Oh, darn. I thought it was going to go higher than that. Oh, you guys can see the steam coming off here? Ooh, that's cool. There's the water, okay? And all these bubbles, that's oxygen gas. And now I got a big mess. Okay, that's okay. You guys don't have to clean it up, right? So that isn't, and I'm not going to show you how the electrons transfer yet, but I will. We'll get a little deeper into it. So that's an example of an oxidation reduction reaction. And let's do another favorite of students. You guys know what HC3H8O is? Not quite. Ethanol has 2 carbons. This is propanol, or let's see this. Isopropyl alcohol is another name for it, or rubbing alcohol. So you guys can do this at home. You need oxygen to burn, right? And what happens when we burn stuff? We get carbon dioxide and water. Oh, I forgot. This is called a synthesis reaction. This is called a decomposition reaction. You understand why it's called decomposition? It decomposes, breaks down into different components. Okay? It's kind of the opposite of synthesis. So that's a way to tell that it's an oxidation reduction reaction. And this one right here is called a combustion reaction, because we're burning stuff, right? Burning a carbon-hydrogen compound. And every time we burn a carbon-hydrogen compound, we will always get carbon dioxide and water. Of course, if you have some other stuff in it, like wood, wood's a carbon-hydrogen compound, but it has other stuff in it. That's why we get ash, right? But, okay. Guess I don't need these for this. I didn't need it for that either, but okay. And isopropyl alcohol, most of it's 70%. 70% what? Alcohol. So this is called the rubbing alcohol. 70% isopropyl alcohol, the rest what? Water, okay? So we'll just put some in here. What the heck? We're not driving. Wait. Okay. What was in here before I put this isopropyl alcohol in it? Air. What's in there? Oxygen. We have to have the oxygen, otherwise it won't work. We can only do this experiment one time in a row. Why? Because then there's no more oxygen. It takes a while for oxygen to fill with oxygen. And why am I spinning it around? To what? To evaporate the alcohol. Right? You guys put out rubbing alcohol in your hand, it evaporates quickly, right? Is water flammable? No, this is 30% water, so we're kind of just getting the alcohol to evaporate. Okay, let's. You guys care? Why did that do it when I put that in there? Because it got rid of all of the the pressure in there, got rid of all the atmosphere. You push it on there, there's more pressure out here, so just, okay? A little physics with the chemistry, doesn't hurt anybody. It's coming, there's the water, okay. And of course, carbon dioxide went in the air, can't see it. So that's a combustion reaction. You guys hate this? We should just talk, right? Okay. Okay, and the last one, I brought some today, and I normally don't because it's messy and it's, anyway, deals with acid. So if you're sitting on the front row, sorry, no. So the next one is a single replacement reaction. And we have, let's see, so, oh yes, single replacement reaction, and it's where we have an example. Oh, I didn't get this one ready, so it'll take a minute. You guys care, or should we just not do it? Scrap it? Oh. All right, so we got aluminum, and I have some aluminum foil. Maybe while I'm, let's see, I didn't even bring it. Oh man, I can't. I'm prepared on this one. I have a little pair of scissors. Does anybody have a big pair of scissors? Darn it. I was thinking when I grab this, I could get it ready, or I could just bring it and we can cut it in class and whatever. But I forgot scissors. Oh, I got some. You have some scissors? No? I'm prepared. I'm just kidding. Want to be cutting that? Cut it in small pieces. They're just little teeny pieces. Or you could tear it. Maybe you could tear it. Maybe tearing is just as good. Okay, this is some high concentrated hydrochloric acid. Sure, yeah, but tiny pieces. Oh. This one I have to wear glasses because we're dealing with a high concentrated solution of acid. I had to get some little girl hair bands.
That's enough?
Maybe, but we need it way smaller.
Oh,
Tiny, tiny, tiny. Why tiny? Why do we have to have tiny?
yes, because of exploding.
We don't. We could just do a big chunk of aluminum, that's fine, but why tiny? More surface area to react more at a time. Then we don't have to wait all day. Well, it looks like we have to wait all day anyway. Cut this out, right? Okay. Had to buy all that just for one balloon. Oh my gosh. And I had to buy all these for one rubber band. Anybody wear braces? Has an extra brace rubber band? That's what I always ask my students. There's always, in high school, there's always someone with braces, so. am I putting a balloon on here? Oh, I didn't even show you this reaction. We have aluminum with hydrochloric acid, and well, this aluminum kicks off the hydrogen, and we get aluminum chloride, and we're left with hydrogen gas. And yeah, I know it's not balanced, but this balloon here is to collect the hydrogen gas.
Plus hydrogen.
And I'm just going to put this rubber band on there so that it stays on there pretty good.
Is this hydrogen 2 or?
Yeah, H2, this is a diatomic molecule. That's probably good.
Yeah, that's the piece. Here's a few more.
All right, I'll do this right here. Can everybody see this? And I'm gonna just plug this right here so that no gas gets out of it. And it might bubble over and we'll see. Oh, you guys want to get rid of nose hairs? Anybody? All you have to do is put your nose over this high concentrated hydrochloric acid. It will burn your nose hairs out. Anybody? Oh, no. It'll hurt though. Okay. Oh, you can see it going already. Oh, there you go. Uh-oh. Oh no, oh no. That's a waste of hydrogen gas, darn it. Hope this balloon doesn't pop. And that black stuff is the aluminum chloride. We need more gas to make this flow. Oh, sorry about that. So, like helium, hydrogen is lighter than helium. Sorry, is it burning your nose already?
Yeah.
I'm sorry. Will you forgive me? Okay. Well, it's kind of floaty, but the balloon's heavier than the gas, so. But this is really warm, so this is an exothermic reaction as well. So maybe I shouldn't do this one ever again? We'll see.
It's not that bad.
Well, what do you know about hydrogen gas?
Thanks.
It's one, oh yeah, no, that was the aluminum chloride. Okay, or it might have been residual hydrochloric acid. But hydrogen is flammable. So, ready? Oh, that wasn't very cool. We should do a slow-mo video, right? Oh, if you have a bigger balloon, get more hydrogen gas. Oh, that's cool. So that wasn't way cool, but okay. Good enough? All right, so those are the 4 types of oxidation reduction reaction. Why do we call this one single replacement? Because this compound there's only one atom that gets replaced. The aluminum replaces the hydrogen, leaving aluminum by itself. That's why we call that a single replacement. Are we good?
What is this liquid left? Just liquid?
There's probably water. It might be a little bit of acid in there too still. It might not have all reacted. Did I measure it very well? No, I kind of just dumped, right? Okay. So maybe if I would have measured, we wouldn't have had that bad experience. I apologize. All right. So any questions with oxidation reduction reaction?
Can you go over again why that one is single replacement?
Yeah. So this guy's not being replaced. He's replacing hydrogen. You with me? And then hydrogen is all alone, kind of like aluminum was. So this hydrogen got replaced. There's just one element in one compound that gets replaced. Single replacement. One means single.
So
Good.
H2 that you put in the bottle, it gets replaced.
I put HCl in the bottle, and it reacted with the aluminum and made aluminum chloride and hydrogen gas.
So hydrogen gas was separated, that's why.
Yeah, we got the hydrogen gas in the balloon. Uh-huh.
Where did you find the HCl3? How did you get this 3?
How did I get this? Oh, I can balance this. Because if we have HCl, do we just have one hydrogen atom and one chlorine atom? No, I poured a bunch of that stuff in there. How many molecules of HCl are in that thing of that bottle of acid? Trillions and trillions and trillions of them. So I'm going to have more than 3. But why does 3 hook up with aluminum? Because aluminum is a 3+ ion, right? Chlorine is a 1- ion. You swap the charges, right? That's why we get it in that form. That's the only form aluminum chloride can come in. Make sense? Okay. So let's talk about precipitation reaction. I only have one for this one. Now, here's an easy way to remember or to determine if a reaction is oxidation reduction or not. The other 2 types of reaction, precipitation and acid base, those are double replacement reactions. So we talked about a single replacement reaction. A double replacement reaction is going to have 2 ionic compounds in solution, in water solution. Did we talk about what water solution is? I thought we did last time. So aqueous, did we talk about aqueous? Okay, so if we have, if we have PbNO3 in parentheses and a 2, what's that called? Can anybody tell me what that substance is called? What? Almost. Lead is one of those that are variable. Remember that? So that's lead 2 nitrate. It's not 2 just because of that. You swap them up, or if you figure out the charge, it is positive 2, right? So lead 2 nitrate. And this is a water solution of lead 2 nitrate. We're going to add, kind of like I added to this hydrogen peroxide, potassium iodide as an aqueous solution. And double replacement means these guys are going to swap places or swap partners. It's kind of like what goes on in today's, well, we decided we get married and say, you know what, you're not for me. And we get a divorce and go find somebody else's, right? I don't know, just saying. So they swap partners here. And well, what do we get? So lead hooks up with iodine. And this is where you're going to have to use what we learned in exam 2 material to find out, to predict the product here. So what is lead 2 mixed with iodine going to give us? Somebody tell me the chemical formula right now. Lead 2 plus with iodine. Iodine is a 1- ion, right? Because it's in group 17. Are we? But I might be wrong, so I don't want to say anything. This is your practice. Y'all take the test yet, the exam? This is good practice for that. If you have lead 2 plus with iodine, what do we get? PbI2, that's it. And we also get what? Potassium hooks up with nitrate and becomes What's the charge of potassium? What's the charge of nitrate? Cross the charges, simplify. So, nope, potassium hooks up with nitrate, so it's going to be called potassium KNO3. Do we need that 2? Does that 2 carry over? Why is that 2 right there? Because it was hooked up with lead 2 plus. You with me? No? Questions? All right. Turns out potassium nitrate is aqueous and lead iodide is a solid. It does not dissolve in water. So we talked about that there are some ionic compounds that do not dissolve in water. So let's okay, here I have, what does that look like?
Like water.
Water. It's a water solution of lead nitrate, lead 2 nitrate. Put a few in here. Just so we can see something here. There it is. And I've got another aqueous solution. This is potassium iodide. Still looks like water. Okay. Can you all see this from where you're sitting? Yeah, that's right. Okay, that yellow stuff is a solid. And in just a minute, it'll just settle down to the bottom. Okay? If we put it on a centrifuge, it would settle faster, right? So this is a heterogeneous or homogeneous mixture? Heterogeneous, right? Settling out. Okay? If we shake it up, then it will look like homogeneous, but just for a second, then it's going to settle right out. Yeah? Okay, it doesn't look cool right now, but after a while, I'll show that to you, and it'll be clear at the top, and all the yellow will be down the bottom. Oh, I should have brought something. All right, any questions with precipitation reaction? Maybe I'll give you a definition here. Precipitate. You guys ever heard of precipitation? When do we hear it? On the weather channel? Oh, we got high precipitation, right? Well, what is he talking about? Or she? Nothing really? Something. Some sciencey junk, right? Raining, right? It's going to rain. Well, what has to happen for it to rain? We got to have clouds, right? And, well, did that look kind of cloudy when I mixed them together? It kind of clouded up, right? Well, precipitation in chemistry is when two aqueous solutions form an insoluble substance. What does it mean to be insoluble? Does not dissolve. That means it's just going to be a solid. So when two aqueous solutions form an insoluble substance, or in other words, a solid.
I guess that's why I was confused, is they aren't referring to the rain, it's not solid, right?
Yeah, it's not. But that's why I say in chemistry, but it's kind of similar,
Yeah.
where it kind of clouds up, right? Okay, but yeah, we're dealing with gases and, yeah, okay. Okay, one more. This one's not as cool. Well, that one wasn't as cool, but it was ish cool. Okay. The last type of reaction we're going to talk about is an acid-base reaction. And an example, in fact, how do you know if something's, in fact, we'll get into this a little bit deeper. We'll just give you the example and then get in a little deeper a little later. So if we have hydrochloric acid, and again, it's an aqueous solution, otherwise it's not an acid. Okay, it's just an ionic compound. And we mix it with sodium chloride as an aqueous solution. This is our base. So this H tells us it's the acid, and this hydroxide tells us it's a base. And we'll talk a little bit more about that. In fact, we'll get way deeper into that in chapter 10, the end of the semester. Right now we're just dealing with one type of acid-base reaction. And we will get, well, what do you think? Can you predict what we'll get? This is a double replacement reaction. The two cations swap partners. Yeah, we get water, H2O, HOH, right? HOH is just H2O. You with me? And it's a liquid form of water. Do we put aqueous as water? No, aqueous is a solution of water. That means it's something mixed in water, something dissolved in water. Water's not dissolved in water, it's just water. So we call that liquid. And then sodium hooks up with chlorine and we get what? Salt. Should we call that a salt? A solid?
Salty water.
It's mixed with water, so we're just going to call it aqueous. Does that make sense? Okay. So another name for this reaction is a neutralization reaction. Because you saw me pour that hydrochloric acid in there to make that reaction with aluminum. And it kind of affected some of the ladies on the front row here. And so hydrochloric acid, that's bad stuff, right? Very corrosive substance. Sodium hydroxide is also very corrosive. If you were to drink hydrochloric acid in high concentration, you would die. Or if you got it in your eyes, you would go blind. Same thing with sodium hydroxide, yeah.
On the formulas, does always like the first element mix with the last one?
Yes, because remember, if this is an aqueous solution, these are ionic compounds. So the cation cannot form a bond with another cation, right? Because they repel. So remember what happens, we'll talk about this a little later. These things dissociate, and then they say, hey, I want to hook up with that guy. So they come over here, hook up, and then they either don't hook up or they do. In this case, they do, and we get water. Do these hook up? No, they're still dissolved in water. They're still dissociated. We talked about dissociation, right? Okay? But in this one up here, oops. Come on. This one hooked up. That's why we got a solid. This one did not hook up. It stayed separated in solution. That's why we didn't see anything besides that yellow solid. Okay? Oh, I should have brought one more. I'm going to have to dump this out. You guys can see it's a little bit less foggy on the top. I don't know if you can see that from where you're sitting. And it's a little darker on the bottom. So that really is a yellow solid. let's. That's not how you get rid of them, I'm just. All right. Uh-oh, uh-oh. Might not be able to do this one. Come on, nuts. Can't do this one, ladies and gents. It's not gonna, you're not gonna see anything if I don't have another substance. What happened to it? I must have just not put it in. I had it and then I just didn't put it in, I guess. Darn. That's okay. It didn't look cool. Here's just to show you that if I take the hydrochloric acid and mix it with just the right amount of sodium hydroxide, both corrosive materials, then I could drink it when I'm done. I wasn't going to, but I could. Because what is it? What did it make? Salt and water. So I could have, but I probably wouldn't in this situation because this isn't very highly measuring chemistry. So, well, sorry. All right. Any questions? So those are the different types of reactions that will come across. How do you tell if it's an oxidation reduction reaction? Easy way. If it's not a double replacement reaction. If it is a double replacement reaction, it's either a precipitation reaction or an acid-base reaction. How do you tell if it's an acid-base reaction? If it has an acid and a base, and we get water and salt. That's it. How do you tell it's a precipitation reaction? We get a solid forming out of the two liquids, or the two aqueous solutions. So those are the two types of double replacement reaction, and if it's not, it must be an oxidation reduction reaction. Or you can memorize all of these ones. I just gave you the easy route. We good? Okay, on your worksheet that you picked up last time, let's pull that out. So on section 2 of the bottom page, or the first page, then it says classify each of the following as oxidation reduction, precipitation, or acid base. What does the first one look like?
Look like molecule.
There's a bunch of molecules, that's right. What kind of reaction is this?
Aqua.
There's aqueous in there. That means it must be what? A double replacement reaction. Can you see that that's a double replacement reaction, guys? Look at it. Do you have that in front of you? Anybody need it? Yeah.
The oxidation reactions is like the first three that we just saw.
Uh-huh.
And
First
the
four.
Reduction, first four. And then the reduction is like from double to bottom.
So,
The reactions to like the last ones.
so double replacement is the last two. Uh-huh. Either precipitation reaction or acid-base reaction.
And those are reduction.
Oxidation reduction reaction are not double replacement.
Oh.
They're all of the other ones, the first four that we did. So look at this first example, calcium hydroxide, dihydrogen sulfate, or you might want just hydrogen sulfate, creates or produces calcium sulfate and water. What is that? Acid-base reaction. Our acid is our H2SO4. We got the H in front. That tells us it's an acid. When hydrogen is the cation, we're dealing with an acid. If it's an aqueous solution, we can see that it is.
But
And if hydroxide is the anion, the OH is the anion, that is the base, if it's an aqueous solution.
but it says it's water, it's not
Sure, we're making water. And what's calcium sulfate called, besides calcium sulfate?
magnesium sulfate.
Salt. All ionic compounds are salts. You with me? No? Far from me?
Calcium sulfate or
Well, calcium sulfate is an example of salt, and then we have water. If we end up with salt and water, and we started with acid and a base, that's an acid-base reaction, or a neutralization reaction. Are we good there?
Sorry,
Yeah.
that's not a double replacement?
It is.
It is.
Do I need to draw it out and show you?
So, well, sorry, I can see that it is, but didn't you just say, maybe I misheard you, but acid-base reactions aren't double?
No. If it's not a double replacement reaction, then it must be an oxidation reduction reaction.
Okay, I think I just misheard.
Okay? If it is a double replacement reaction, it's either acid-base or precipitation. And how do you tell the difference? One produces water, one produces a solid. Rebecca.
How can we know which one is the base, which one is the acid?
Okay. Acid is the one with the H as the cation, the hydrogen as a cation. So it's the first element on there. And base is where we have hydroxide as the anion. Now, there's other bases besides that, but this is a strong acid and a strong base. And when we have a strong acid and a strong base, we can neutralize it and get salt and water. And we're just keeping it simple right now. We'll get deeper into acids and bases in chapter 10. Okay?
after that we go deeper.
Yep. Okay, do you think we got this?
Last one,
Okay, what about the second one? H2O2 gives us H2O and oxygen. We just did this in class. What type of reaction is this? What? It is decomposition, but that's not one of the options it gives us. Either oxidation reduction, acid base, or precipitation. What? It's a redox reaction or oxidation reduction. How do we know? It's not a double replacement reaction.
that's
Write that down.
decomposition reaction.
If reaction is not a double replacement reaction, then it's oxidation reduction. That's the easiest way to tell.
What is it, double repetition?
Double replacement reaction. I'm feeling like we're not getting this.
Reaction.
How are we, talk to me. Yeah,
So I just want to be sure, so, the redox reactions, like only one of them was specifically named a single replacement? Are all four of them single replacements?
no, all four of them are redox reactions.
Okay, but only one is a single replacement.
Yeah. And the only type that's not under oxidation reduction is a double replacement reaction. So if we have a double replacement reaction, we have two ionic compounds that are in aqueous solution, and they swap partners, that's a double replacement reaction. And if we have a double replacement reaction, then it is definitely not. And should I prove it to you? Maybe make more sense? Oxidation reduction reaction is when we have a transfer of what? Electrons.
Is this reflection or reaction? The oxidation?
Oxidation reduction reaction. Okay? So we have HCl plus NaOH, this is the one we just did, gives us H2O and NaCl. Okay, let's figure out, these are all ionic compounds. What's the charge of the H? +1. What's the charge of the H over here? It's still +1. What's the charge of the chlorine? -1, or 1 minus, right? You with me? Do you understand what I'm doing? Yes or no?
Yes.
No? Okay. Remember when we did ionic compounds? Ionic compounds, a metal and a nonmetal, or a cation and an anion. Once you get the cation and anion, you get the charge and you cross them and you get your ionic compound, right? All of these are ionic compounds.
What is it?
Oh, that one's not.
OCl? The
What?
second one is NaOCl.
NaCl,
No, this one.
NaOH.
Na.
Okay? And what's the charge of sodium in sodium hydroxide? You guys understand where I'm getting this +1 from?
Yes.
The periodic table, it's in group 1. It's going to lose 1 electron. Chlorine is in group 17. It's going to gain 1 electron. Right? This is stuff that we learned last unit that we're going to be taking a test on this week. You ready? And hydroxide is a polyatomic ion, -1. And then over here we have sodium, which is +1 and -1. What happens to the hydrogen? And we can look at this as HOH, right? It's not an ionic compound, but okay. Nothing happens. It doesn't gain or lose, does it? Does it? Stays the same. You with me? What happens to chlorine? Stays the same. No transfer of electrons. Sodium, no transfer of electrons. Hydroxide, no transfer of electrons. Sorry, that should be, that's a -1. Okay? Since we don't have a transfer of electrons, this is not an oxidation reduction reaction. Do we have to do that every time? No. If we can see that it's a double replacement reaction, we should know it's not an oxidation reduction reaction. If it's not a double replacement reaction, most likely it's an oxidation reduction reaction. Good?
Can you go over the transfer of electrons that takes place in the combustion, and the single replacement reactions?
Not yet.
Okay,
Okay? Right now we're just keeping it simple.
okay.
Because right now this just says, which type of reaction is it? Okay? So let's look at the next one. H2O2 goes to H2O plus oxygen. Is that a double replacement reaction? No, I hope that we can see it's not. Two things don't get replaced. They don't swap partners. Well, there's only one substance on the reactant, right? So this is what type of reaction? Redox reaction or oxidation reduction reaction. Are we good?
Or
Okay.
decomposition reaction.
Sure. But if you read the instructions, it doesn't say decomposition reaction on there. You with me?
Yeah, I'm asking.
But all decomposition reactions are most likely oxidation reduction. Okay? And what about the next one? HCl with silver nitrate makes HNO3 and silver chloride. It is a double replacement reaction. That means it's not oxidation reduction. What are our options? Acid, base, or precipitation. Which one is it? How do you know? Because it produces a solid from two aqueous solutions. Can you see that? All right, why don't you guys try the rest of them? And if you have a question, please raise your hand.
Double replacement reaction, you see,
Do you understand how to see if it's double replacement?
because it's CN plus and it's easy as you mentioned, double replacement reaction.
Here's how you know it's double replacement.
No, this
Because
hydrogen.
hydrogen, so I'm just breaking the cation and the anion, right? This silver was with nitrate. Now it's with chlorine. It replaces hydrogen. What does hydrogen do?
Let's go
It
out.
replaces silver and hooks up with nitrate.
It's
We
because
got
of
two
electronegativity.
replacements. No,
Electrons.
it's, well, sure, you can, we're not worried about why right now. I just want you to recognize this is a double replacement reaction. This guy comes over here and kicks off silver, and silver comes over here and kicks off and replaces hydrogen. Hydrogen replaces silver. We've got two replacements. Double
The
replacement.
first one you say decomposition reaction is not
Sure.
double replacement.
No, it's not. This is the decomposition reaction, but that's not one of these options.
Yeah, but it's also an oxidation
Yes.
reaction. I have to read about it.
Yeah. Are we good? How are we feeling?
You weren't wrong, because you weren't right. Okay, let's do the next one.
We ready to move on? You want to go over some?
Yes, please.
Yeah, which one?
Last,
Last one? Yeah, because it doesn't have a, so it's supposed to be barium chloride. With sodium nitrate, or sulfate, I mean, gives us barium sulfate as a solid, plus sodium chloride. And the rest of these are aqueous. Since we have two aqueous solutions, and they do swap partners, we end up with a solid. What kind of reaction is this? Precipitation reaction.
Can we go over the second last one?
Yeah,
what kind of reaction is it?
It's a precipitation reaction
The Cl goes with nitrogen,
because we get a solid
precipitation.
like the yellow one. Remember that demonstration we did?
Precipitation reaction.
Okay. Next,
Precipitation.
we got C4H10O2 plus O2 gives us carbon dioxide and water. Is this a double replacement reaction? It's not. See, they don't just swap partners here. So what does it tell us it is? Oxidation reduction reaction. Yeah, that's it.
Could we potentially look at it as, because you went over the combustion reaction.
This is a combustion reaction.
Right, 'cause-
Yes,
And do they always end in carbon dioxide and water?
always.
So we could potentially look at it and say it's a combustion, therefore it's an oxidation?
Yes, you could. So if it's any of those four reactions, that's one way to do it. If it's a synthesis reaction, a decomposition reaction, combustion reaction, or a single replacement, it's oxidation reduction, most likely. Why do I keep saying most likely?
Because
There's gonna be some examples where it's just neither. It's none of them. Okay? But for now, we're just keeping it simple. Any other questions? Okay, we have 4 minutes till break. Do you want to take break now? Or do you want to go for 4 minutes and then?
What about?
I think we should take a break now. What do you think? Okay. Sorry, some of you are looking like, come on, go, go, go. I get it. But more important than just getting crap done is to make sure we all get it. If you have any questions during break, feel free to ask.
Come back with, come back with 21. New topic.
Yeah, no, not it's. Now we're going to go a little bit deeper into all of these reactions. Okay, so the first type we'll talk about is oxidation reduction.
First, no.
Oh, man. I'm sorry, everybody. I didn't take my break.
Really, is it only?
Because I think that's the key, like if we made steps, that would be the best. So let's use NASA.
Pakistan, general,
So,
visit Trump.
so I just look for H3.
Yes, I did before.
Oh wait, the H is no longer with the
General
CO.
Assembly.
I don't care.
Or is no longer with the OH.
Okay, I'm sorry about that.
With the PO.
Okay. So like we mentioned before, atoms that gain electrons is what? Yeah.
Can we get an example of the synthesis oxidation reduction?
Now, don't worry about so much. I'm not going to test you on synthesis, decomposition, and I just gave you some names to kind of help you to relate with it. But yes, I can give you an example of that. Let's go through what an oxidation reduction reaction is, then we'll go through a lot of examples. Sound good? Okay, atoms that gain electrons we call what? Oxidation or reduction?
Oxidation.
Gaining electrons that makes it more negative is reduction. So its charge goes down, reduction in charge, right? And then atoms that lose electron are then and again, oil rig if it helps. There's also another one that says Leo the lion says grr. I never liked those things, but some people like them, but that's okay. Are we good?
Atom that neither is doing neither of them, what's called?
What's that?
If atom not losing, not gaining, what does it call?
Not oxidation reduction.
Not losing, not gaining.
If it doesn't lose, so if you have an oxidation, you will always have a reduction. If you have a reduction, you will always have an oxidation. If you don't have those, it's not an oxidation reduction. That's all you need to know right now.
That's
Okay.
it, Joe.
That's it. Okay? And then it's probably a double replacement reaction. And if it's not a double replacement reaction, then it's just a different type of reaction we're not even going to talk about. Sound good? This is just elementary chemistry. We are not going a mile deep. Okay? So if you want to go deeper, you take a higher course. Okay? All right. So for ionic compounds, we can see that that's pretty straightforward, I hope. Yeah? Just the charges will change. It goes from 0 to +1 or -1 to 0 or whatever. Okay? But then let me give you some rules. For the rest of them, for non-ionic, you kind of gotta follow some rules or some standards to make sure you know what it is, or to make sure it is an oxidation reduction. So here we go. We need to find the oxidation number. And here are the rules, or the things that help us to determine the oxidation numbers. So the first one is, if the element, in fact, we kind of talked about iron being oxidized, right? Iron or magnesium being oxidized. That's why we call it the oxidation reduction. Does it mean the element besides oxygen is deoxidized? Can oxygen ever be oxidized? Yes. Okay. So, but the reason we called it in the first place the oxidation reduction reaction is because back from the beginning of time we dealt with metals, right? And metals what? Oxidize. And when they do that, well, they lose reactions, they lose electrons, and the other element gains electrons. Okay? We good? So let's go through some examples to determine the oxidation number. So for neutral atoms, or neutral atoms, then, so they're all alone. Has an oxidation number of, I'm going to just say OX number. Is that okay? OX number stands for oxidation number. And that has an oxidation number of 0. Why? Because it's neutral. Make sense? Okay? Any questions on that one? So, diatomic molecules are all alone, even though they're with another of them their own, right? It's just the elemental oxygen does not exist, so we call it O2. The oxidation number for O2 is 0. The oxidation number for Cl2 is 0, and so on. Okay? The next one, ions in ionic compounds. their oxidation number is equal to the charge of that ion. Just kind of like we demonstrated earlier. So those are pretty straightforward. Now we're getting into, well, what if it's not an ionic compound? Okay. This one also goes with everything, but the sum of the oxidation numbers in a compound is equal to the charge of the compound. What's the charge of all ionic compounds? Do we know that? They're all neutral. So the charge is 0. That means the sum of the oxidation numbers has to add to 0. And we kind of already dealt with that with ionic compounds, right? Okay. But for a covalent compound, do all covalent compounds have to have a charge of 0? What's an example of one that doesn't have a charge of 0? Starts with a P. Ends with atomic. Polyatomic ions are charged covalent compounds, right? And so the sum of those oxidation numbers of those elements in that polyatomic ion is going to equal to the charge of that polyatomic ion. You with me? Okay. And then here is the big one you need to know. For covalent compounds, use the following oxidation numbers in the exact order I give you them. Use the following oxidation numbers in exact order. Okay. If the covalent compound has hydrogen in it, this is the first one we're going to look at. We're going to ask ourselves, is hydrogen in it? If it is, then its oxidation number is +1. Do we understand why it's +1? Because it loses an electron during an ionic compound, right? I know this is not an ionic, but we use the same reasoning. So H is +1. Then after that, if it doesn't have H in it, we ask, does it have fluorine? If it has fluorine, what's fluorine's oxidation number? Any guesses? -1. Because it's in group 17, it wants to gain 1 electron, right? To reach the octet. So that's the reasoning, and it kind of just makes sense so that we don't have to learn something new, right? If there's no hydrogen, no fluorine, the next element we check is, does it have oxygen? If it's oxygen, what's its oxidation number? -2. And then after that, we check chlorine, then bromine, then iodine in this order, and these all have an oxidation number of what? -1. So the main thing is you have to follow this order. If we have a compound with oxygen and chlorine in it, you have to do oxygen first. Because maybe chlorine won't be -2, -1. Now for some examples of determining oxidation number. Let's start with the simple one. If we have calcium chloride, what kind of compound is this? This will be good for this exam we're taking this week, right? What kind of compound is this? Ionic, okay. So we should know what the oxidation numbers are. What's the oxidation number for calcium? +2. the difference is we don't call it 2 plus, we call it positive 2. Oxidation number isn't really the charge, but it's just an oxidation number. But basically it's the charge, right? Okay? And what about for chlorine? What? -1. And if you multiply the -1 by 2, you get -2, and you add it to +2, and you get what? 0. Well, that's good because this is a neutral compound. It follows that rule. Make sense so far? Questions? Okay? Let's do another example. Let's do CO3 2 minus. Now we have, this is a covalent compound. Well, it's a polyatomic ion that's charged, right? All right, so we've got to figure this out. Which are we going to check first, carbon or oxygen?
Both. Carbon is not.
No, we don't check both of them first. We can only do one first. You guys ever add things together? Let's say you add 10 numbers together.
Carbon.
How many do you add at a time? 2, right? 2 at a time. So that didn't go against. Never mind. Ignore that comment. Okay.
Carbon is either positive or
No,
negative.
no. We don't deal with carbon. Here's how we do it. We go in this order. This is a covalent compound. Does our compound have a hydrogen in it? No. Does it have fluorine? No. Does it have oxygen? Okay. That tells us the oxidation number for oxygen is what? -2. Now we have to figure out what the oxidation number is for carbon. Notice there's no carbon in here. But even if there was, we still have to figure it out. And here's how we do it. We use this rule right here. The sum of the oxidation numbers has to equal what in this example? -2, the charge of our compound. You with me? Okay. So -2 is equal to the -2 for oxygen, but how many oxygens are there? 3, so that's -6. You following me? Or do I need to show my work? Are we okay?
Just divide.
We're not going to divide yet. Then we're going to add the oxidation number for carbon. I'll just call it X. I don't know what the oxidation number for carbon is. Carbon's not always going to be the same. In fact, oxygen's not always going to be -2. Okay? So now we have to do a little bit of algebra. How do we solve for X?
+6.
We add 6 to both sides. Good. And we got the oxidation number for carbon is +4. You with me? And then it works out. Any questions on that? Okay. Now, in general, I'm not going to give you a compound and say find the oxidation numbers. What I will give you is a reaction. I might say, what kind of reaction is this? You want to check. If it's not double replacement, then you have to check to see if it really is oxidation reduction. And I'll give you an example where it's neither. Okay, here we go. So here's another example. If we have sodium as a solid plus chlorine gas, it gives us sodium chloride as a solid. Just by looking at this, does this look like an oxidation reduction reaction or does it look like a double replacement reaction? It looks like an oxidation reduction. This is a combination or synthesis reaction, right? Okay, it's not double replacement, but let's check it. Let's double check. So we got to find the oxidation number of each component. There's 3 components in this reaction. So what is the oxidation number for sodium? What is it? Not quite. Who can tell me why it's not positive 1? Because it's sodium metal. This is the elemental sodium. And what's the charge of just the elements? 0. So that follows this first one. If the element is all alone, it's 0. Its oxidation number is 0. Okay? What about for chlorine gas? It's also 0. Because chlorine, that's how chlorine exists in nature alone. You with me? So all diatomic molecules are considered to be alone, and their oxidation numbers is 0. And what about sodium in sodium chloride? This is an ionic compound. And how do ionic compounds form? With charges, right? Has to become an ion. So what's the charge of sodium? Ion? Positive 1. So what's the oxidation number for chlorine? Negative 1. Do they add to be 0? Yeah, and it should. Okay, so now we might be asked, which one is oxidation and which one is reduction? I like to start with reduction. Why? Because reduction, we have a reduction in charge. Which one has a reduction in charge, sodium or chlorine? Chlorine. So I say, okay, this one is reduction. And that means sodium is oxidation. See, we don't even have oxygen in this reaction, but we still call it an oxidation-reduction reaction. Are we okay with that? In fact, oxidation-reduction is just a name we give it. That's it. Okay? But we can see this lost electrons and this gained electrons. Good? How are we feeling so far? Okay, let's do more complicated one. So that one was a synthesis reaction. You wanted to know decomposition, is that right, Rebecca? Well, that was a synthesis. Okay. Let's do another one. Let's do a decomposition reaction. So we know this one should be oxidation reduction, right? Okay, if it is, we want to know which one is oxidized, which one is reduced. Notice I give you 2 words there, oxidation or oxidized, reduction or reduced. You get that those are the same? Okay. All right, so what's the oxidation number for potassium in potassium hydroxide? What kind of compound is this? Not all at once. This is ionic because it has a metal in it. Therefore, we just look at the charges. What's the charge of potassium? +1. Oh, hydroxide. Darn it. Hydroxide is a polyatomic ion. The total charge is -1, but we got to find it for oxygen and for hydrogen. Which one should we find first? Look at that list that I gave you. Has to be in this exact order. We have to do hydrogen first. So hydrogen's oxidation number is +1. You with me? And so let's see. Oxygen has to be so that when we add the oxygen's oxidation number and hydrogen's oxidation number has to equal what? -1, just like hydroxide. Or another way to look at it, this compound is neutral, so they have to, all three of these have to add to 0, right? That might be an easier way to go about it. So that means +1 plus whatever it is for oxygen plus another +1 equals 0. So what's oxygen's oxidation number? Has to be -2. Does everybody see that? If you don't, just do the algebra. We can add these two together. We have 2 plus x equals 0. Subtract 2 to both sides. X equals -2. Yeah, Rebecca.
So in the elements of the top, it's like we have the charges, and oxygen says it's -2. So it's always going to be -2? Or it's
No, it's not. That's why you always have to check.
You always stop after the first one that you find
Uh-huh.
in that list.
Yep, and then you figure the rest out. If you have 3 elements in a compound, you might have to check out, okay, what's the next one, right? But in this case, we already knew potassium. Okay, do you have a question?
Yeah, I think I was gonna ask something similar about if you have an element that's not on the list, do you do that after you've already calculated the oxidation numbers for the elements that are on the list? So in this case, like since potassium is not one of the
Uh-huh.
6 on the list, would you do that after oxygen and hydrogen?
No, we did it before.
Does it matter when you do it?
It does. Because this is an ionic compound. Therefore, if we know what the charge of the ion is, if it's a single element, the charge of it, we just put it in there right away. We only have to follow this order when we're dealing with what kind of compound? Covalent compounds. And so in potassium hydroxide, potassium is a metal, and hydroxide, that's a covalent compound, isn't it? It's a polyatomic ion. All polyatomic ions are negatively charged covalent compounds. So now we look at this one by itself if we wanted, right? Or we can put it together and do like we did on this and say that since the charge of this is 0, they have to add to be equal to 0. And if I did it right here, I can do it again. So if hydrogen here in hydroxide is +1, then whatever for hydrogen is, or for oxygen, +1 has to be -1. So we subtract 1, and we still get -2. So it really doesn't matter which way you do it. Okay? We good so far? Okay. Okay, this is an ionic compound. That means it's easy, right? What's the oxidation number for potassium? +1. What is it for oxygen? -2. And we're done. Do we even have to add them? We can check it. 2 plus a positive 1 is +2. And a -2 has to equal 0, and it does. Okay? Now we got to do water. This is a covalent compound. So which one do we check first, hydrogen or oxygen? Hydrogen is +1, and there's 2 of them, so that's +2, plus whatever oxygen is has to equal, what's the charge of water? 0, because there's no charge listed, right? So what is the oxidation number for oxygen? -2. Are you sure oxygen's not always -2? Yes. It is a lot, but it's not always. Okay, so tell me, which one is oxidized, which one is reduced? We have 3 different elements here to choose from.
H2O and
We're not looking for H2O, that's a compound. We're looking for which elements are oxidized, which element is oxidized, and which element is reduced.
H2O is oxidized.
Look at it. Don't guess. Look at it. Does any of them get reduced? Does any of them lose electrons? Does any of them gain electrons?
K.
Yeah, which one? I'm not looking for K2. I'm looking for K. Just the elements, single elements. Potassium goes from +1 to +1. Did it gain or lose electrons? No, it didn't. It stayed +1. What about oxygen? It goes from -2 to -2 here and -2 here. Doesn't change. Hydrogen goes from +1 to +1. Is this an oxidation reduction reaction? No. No redox. So is it precipitation or acid base? No, because it's not a double replacement reaction. So what do we call this? Maybe no reaction, right? This doesn't really happen. I don't know. Because the whole purpose of learning chemistry, ladies and gents, is to make predictions, isn't it? Yeah. Because we want to know if we can make a certain compound. All right, so I did that example to show you. That's why you check to see what the oxidation numbers are. We good? All right. Now let's do one that is an oxidation reduction reaction. We have SO2. What's SO2 called?
The one is oxidation reaction.
What is it? This is a covalent or ionic compound. Covalent. And how do we name covalent compounds? With prefixes. So what's this called? Sulfur dioxide. Oh, we're about ready to take a test on this stuff, right? And we're not taking a test so we can dump the knowledge. We're taking it so we can use it. Okay? We're still going to use that stuff. For how long? The rest of the semester. Okay? Plus oxygen gas gives us, what does it give us? What is that called? Sulfur trioxide. Yeah. Okay. All right, this is not a double replacement, so looks like it should be an oxidation reduction reaction. So let's determine what the oxidation numbers are. Does it matter which substance we start with? It doesn't. I like to start from left because I read from left to right. Okay. So sulfur dioxide. Which one do we check first, sulfur or oxygen? Oxygen. Oxygen has an oxidation number of -2 according to this right here, right? And so what's the oxidation number of sulfur have to be? +4. -2 times 2 is -4. Plus whatever it is for sulfur has to equal 0 because it's a neutral compound. So S has to be +4. Andrew?
I forget, how do we know it's a neutral compound?
Because there's no charge on the compound.
Oh, okay, yeah.
If there's no plus or minus on the compound, it is neutral. Yep. Good question. Any other questions? Okay. What's the oxidation number for O2? Oxygen in O2. How do you know -4? Why? How do you know -2?
There's 2 oxygens needed.
But hold on a second. If we follow the second rule, the sum of the oxidation numbers in our compound has to be equal to what here? What's the charge of O2? We just barely talked about this. It's 0. So what plus what, the same number, is equal to 0? 0. Oxygen is all alone here. That's how oxygen looks like all alone. So its oxidation number is 0. Are you with me? Or are we getting our head wrapped around this a little bit? Okay, keep going. Now let's do sulfur trioxide. So this is a covalent compound, so we look at sulfur or oxygen first. Oxygen again. So what's the oxidation number for oxygen? -2, good. And so what does the oxidation number of sulfur have to be? +6. All right. Why +6? Good. Remember, what's the charge of sulfur trioxide?
4 plus.
No, I don't see any charge right there. On SO3, no charge. Do you see that? There's no positive or negative on the upper right-hand corner, so its charge is 0. That means the sum of the oxidation numbers has to add to 0. So the oxidation number for oxygen is -2, right? But there are 3 of them, so that's -6. Plus whatever it is for sulfur has to equal 0. Do you get that? So we use that one all the time. Make sure you know that rule. So we add 6 to both sides, and that gives us oxidation number for sulfur is +6. Make sense? Question? Good? Good, I like that sound. Oh. Okay. All right. Now, we got to know which one is oxidation, which one is reduction. Let's look at sulfur. There's only two elements here. What does sulfur do? Does it reduce in charge? That means it is oxidation. Oh, look at this. What is that? That doesn't do anything, right? Thank goodness we have another oxygen. That one reduces in charge, reduction. Are we good? So even though there's no ionic compound in here, we do have a transfer of electrons. Okay? Any questions on oxidation reduction? Would you like to try some on your own right now to make sure you can do these? Yeah. We did one. Right here. It doesn't have a charge on it the whole thing, but it has potassium and hydroxide. And so we just took hydroxide and we found the oxidation numbers here. This is a covalent compound. We look at oxygen first or hydrogen first. Hydrogen is +1. There's only one of them, so +1 plus whatever it is for oxygen has to equal -1. And so oxidation number for oxygen in this compound is -2. Does that make sense? Okay, do you want to work some on your own? Just to make sure you can do these?
Do we have any speak?
Yeah, so on this worksheet on the back side,
2.
it says, let's see, assign the oxidation number, so section 3. So we need to assign the oxidation. So I would start with the one that looks the ickiest to you.
Number, last
Now, I can do them on the board all day long. I can. And I will if you want me to. You're not going to get these until what? You do it. You do it. But if you don't feel like you can do it right now, that's when we should do some more together. You talk to me. Okay? Try some. I'll post the answers so that you can see if you're doing these right. Okay, just a second. Just a second. Why are you looking for electronegativity? You don't need to right now.
How to find the oxidation in this here? Just see.
For what?
For example, for this, for any element, oxidation.
This is all by itself. There's no other element with it. That means, so where's your notes? Did you take notes here?
Yes.
Flip it over. Right here. For neutral atoms, that means they're all alone. This is all alone. Right here. It's only hydrogen. Has an oxidation number. Yep. Yeah. And then this one right here, also all alone. Now we have a compound.
Now we have to find the electronegativity.
So if you, this, you can consider this as a ionic compound or covalent.
No, my big question is, I learned how to explain it. For example, this is the one that's zero. This is zero because it's all. Anytime any other any actor, when they get together, then we find the oxidation. But how, when we find the oxidation number, we have to find through this research.
No? Yeah.
Yes.
Yeah.
It says oxidation.
No, that's not what it is.
So for example, it's Cl, how I know that here it's zero.
You don't get this for the test. I would not use that. This one.
No, I just printed extra.
No, but I would practice with this one because this is what you get to use.
Okay, this is.
So this right here, so now you're looking at this one right here.
Oh, sorry, I was trying to get
Covalent
CR.
compound. Covalent compound.
Yeah, because two compounds.
Two non-metals.
It's like, no, only put
And then it says
Use the following.
in order. So we have H and Cl, which we look at H first, right? So it's a plus one.
different.
Because it's here.
So, yeah, because it's in this. These are plus ones.
So now I learned.
Yeah. And now this one, you have to add these and they have to equal what? Zero, because this is charge is what? Zero. Because it doesn't have a charge here.
But here's.
Don't do that. for covalence, you cannot do that. You have to figure it out. It worked out the same in this one, but not always. So plus one, so one plus whatever it is for carbon, we can call it X. So, no, we'll just write it right here. One plus X has to equal, according to this rule, the sum. Do you know what the sum means? When you add them together, the sum of, when you add these oxidation numbers together, it has to equal the charge of that compound. And this charge is 0. Do you see that? And so what does X have to be? Minus 1. Does that make sense?
I know it feels
But if, for
like
example, I'm
backwards.
just saying,
I know.
here's,
But yeah, it's easier when you
here's
just
the
go for
difference.
just
Yeah, we're not looking at electronegativity.
But here's 0.
Sure. Come on. You have to look at it. You gotta follow this order.
Exactly, yeah, this
This order right here.
Exactly.
Right? If chlorine's the only one in there, then yeah, you say it's -1. But if it's not, you have to figure it
Through
out.
the equation, you have to.
Yep. Yes.
It is also here, I think. Let me oxidation reaction.
Yep.
You can,
There it is. These are the rules I showed you. Okay, ladies and gents, how are we feeling? Any questions, or are we ready to move on?
Yeah, time?
Yeah, let's,
This is the last one, I just wanna make sure I'm doing it right.
okay. So the last one, we're talking about sodium nitrate and sodium nitrite plus oxygen. Is that the one you're asking?
Yes.
Oops. All right. So we got to just find the oxidation numbers. Ionic compound, right? So what's the oxidation number for sodium in this compound?
1.
Positive 1.
Yeah. So sorry, remind me why we can do that?
Because it's an ionic compound. For ionic compounds, we just use the charge. So that's that one of those rules that I showed you. So study those rules. Study those. And then we have nitrate. Do you want to stick with this compound being 0, or do you want to take nitrate away and just do nitrate by itself?
I'm not sure what you just asked.
Okay. So this compound right here has a charge of 0.
Right.
We could say the sum of those oxidation numbers has to equal 0. Or we could say, all right, the other ion is a -1 ion. We could take sodium or nitrate
Oh, you can do it.
and
Okay.
and do it separately.
I didn't realize you could. Okay.
Either way works. Which way do you want to do
I
it?
guess the way I was doing was just checking the little list of them, so like O's.
Yeah, let's do that. So let's do, oops. Okay, now we got to check out of this covalent compound, which one do we check first, nitrogen or oxygen? Oxygen has an oxidation number of -2. Do y'all understand why it's -2? Because it's in group 7 or 16 and needs to gain 2 electrons. That's the reasoning, but it's not what happens really, okay? And then we got to add all of these. There's -2, but there's 3 of them. That's -6, plus whatever it is for nitrogen, plus a +1 has to equal the charge of this compound is 0. Are we okay with that?
Yeah.
Okay? So we add the positive 1 and the negative 6, it makes negative 5. We add 5 to both sides. And the oxidation number for nitrogen is plus 5. Are we good?
I think I just forgot about the 3 to multiply it.
Yeah, you must. You want to keep going on this one?
Sure.
Okay. What's the oxidation number for sodium over here? Still positive 1. And then we do the same thing here.
Two now.
Oh, that's a 2 though. Good. So the oxidation number for oxygen here is negative 2. There's 2 of them. That makes negative 4 plus whatever for nitrogen plus 1 equals 0. So X has to be equal to positive 3. If you do the algebra, that's what it gets out to be. And what's the oxidation number for oxygen in O2? 0. Good. I think we got it that time, right? All right, so which one is reduced? Nitrogen goes from positive 5 to positive 3. So nitrogen is reduced, a reduction. And which one is oxidized? Oxygen goes from negative 2 to 0 right here. Does that make sense? Okay, one more thing with oxidation reduction before we move away is the reduction is also called the reducing agent. The oxidizing agent. You guys know what an agent does? Like an agent that sells houses, they're a house agent, right? Does that mean they're a house? No, they sell houses, right? They're not the house, they sell houses. They give houses, they don't give them away, but, right? And which one causes oxygen to be oxidized? Nitrogen does. So nitrogen is the oxidizing agent. I know that seems a little confusing at first, but oxidation is called what? Reducing agent. I think you'll find that on homework more than the exam. But just so you know what that means. Okay? We good with oxidation reduction? Yeah.
For the second to last one, the H2O2, do you solve that one with the X, or do you just put the negative 2?
So which one are you talking about? Oh, I'm on the wrong page. The H2O2 to H2O to O2?
How do you solve the first one? Do you
All right.
use like X, or you just put negative 2?
Yeah, you could. I'm just using X. You don't have to use X, right? But watch. Which one do we deal with first, hydrogen or oxygen? Hydrogen is plus 1. There's 2 of them, so that makes positive 2, right? Plus whatever is for oxygen, but we have to multiply that by 2, don't we? Do you see how we do that? Because there's 2 of them, and the total should be 0. What's the charge of H2O2? There's no charge, so it's 0. Good? So now we minus 2 to both sides, and you got 2x is equal to negative 2. So now we divide 2 to both sides, and we got x is equal to negative 1. Oh my gosh. The oxidation number for oxygen is not negative 2. You see that? Yeah, good. I'm glad we went over that one. Do you have any other ones you want to go over? Okay, let's see how we're coming along. This is taking a little bit longer, but that is okay. 100% okay. We are still on cue. We just don't want to get further behind. So, should we I think we should probably call it a day. And then, but here's the thing, ladies and gents. If you don't go home and practice this, study this, you will forget it. How do I know? I've been teaching chemistry for 16 years. That's what happens. This is not normal stuff. You don't deal with this stuff on an everyday life. So if you don't study this and practice it and get good at it, it will leave your brain. And then you'll say, now what do I do? So if we leave today, your homework is to get good at it. I give you extra practice on this worksheet. Do mastering chemistry as well. Study, study, study. Study those rules. Study the techniques that we showed you today. And get good at it. Get good at classifying the different types of reactions. But that's going to help you the most. If you don't do it, you're just digging a hole for yourself. Okay? Andrew.
Going back to classifying the reactions,
Uh-huh.
can we do an example? Because there's one that was a little bit different.
Yeah, which one?
I got the answer, but the fifth option is H3PO4 aqueous.
Okay, yeah. H3PO4 aqueous plus NH4OH aqueous gives us NH4 aqueous plus H2O as a liquid. Okay, there's a couple things in here that tells us what it is. We get, what is this called? Besides the name? Ionic or covalent? How do you know it's ionic? It's made of ions, 2 polyatomic ions. This is an ionic compound. In other words, that's a salt. All ionic compounds are called salts. And we have water. We have salt and water. It must be a neutralization reaction, or what else is that called? Acid base. But that's one way to tell. Here's another way. We have H plus as the cation. And over here, we have OH minus as the anion. This is the acid, this is the base. That's how we tell if it's an acid and a base. Makes this an acid-base reaction.
What threw me a little bit was I was just looking for the double reaction.
Yes, this is a double replacement reaction.
And then I think I got a little confused because the H's and OH's kind of combined.
H hooks up with OH, and NH4 hooks up with PO4. They swap partners.
Right.
Yep. Double replacement reaction tells it's either precipitation or acid base. We know it's not a precipitation because it doesn't form a solid.
And the reason OH and H3 make H2O is because the OH is a...
H plus and OH minus gives us HOH, right? How many hydrogens are there? How many oxygens are there? Yeah.
It just wasn't as obvious that
Yeah.
they swap.
But all acid-base reactions that we're doing in this unit will always produce water and salt.
This plus H2O
Uh-huh.
plus H2.
H2O is a liquid. Yep.
Sorry, one other
No.
thing to clarify.
You're
But,
good.
The NH4(3), sorry, I forget what's called, ammonium?
Ammonium?
Yeah. That's a cation in this case, right?
Yep.
I thought polyatomics were always negative, no,
Not that one.
on that one, okay. Sorry, earlier you said like polyatomic.
All of them are except for that one.
Except for
Well,
that one.
that one and this one.
And
Boy,
that
that's
one,
not a
right,
polyatomic ion.
Okay,
Sometimes it's written like this.
okay.
But we're not going to get into that until chapter 11. Sorry, chapter 10.
Thank you.
Uh-huh. Anything else? Yeah, Rebecca.
I'm so confused in the one I told you because I don't know which one is reduced and which one is oxidized.
H2O21?
Yeah, 'cause,
Okay. Let's go back to this. So let's do this one. H2O2 gives us H2O and oxygen. So this we found to be positive 1 and this one's negative 1, right?
Yeah.
We come in water, this is positive 1, this is negative 2, and this one's 0. Yeah, this one is a little confusing. Which one is reduced? Uh-oh. Oxygen goes from negative 1 to negative 2. Reduced. Which one is oxidized? Oxygen loses an electron. Oxygen is oxidized and reduced in this reaction.
So it's not, doesn't need to be always all the elements.
No. So hydrogen stays the same, doesn't it? Yeah. Good. But it's still true that the rules that tells us it's oxidation reduction still follow. Anything else? Yeah, Lucas.
Yeah, in some of the previous reactions, we see hydrogen ions acting as an acid and hydroxide ions acting as a base. But in a lot of these, hydrogen is just neutral. So is hydrogen always something to look out for in like acid-base reactions?
Yes. Well, if it's just H2, if it's just H2, is that an acid? No, that's all by itself. What about this? What about H2O? Can it be written like that maybe? Oh my gosh. It could be an acid and a base? Don't worry about it this unit. We'll get there in chapter 10. But yeah, if it has not just hydrogen, but if hydrogen is the cation, it's an acid. That compound is an acid. Good? And if hydroxide is the anion for this unit, it is the base. In fact, that's the only strong base we have, so that's why we use it. Good? Any other questions? Okay, have a fantastic weekend.